Good morning. This is the fifth lecture on X-ray crystallography and solid state chemistry. This lecture is in English, but we do have a Bangla version of this lecture in the link below. Now we go to the fifth lecture, and this slide I was discussing in the last lecture, that is fourth lecture, and I do have one point to clarify here. We were talking about that not only the cell parameter which defines 7-crystal system, we have to take lattice symmetry also, and with lattice symmetry and cell parameters, and as well as space lattice, that is Bravais lattice, we define completely the crystal systems. I say about pseudosymmetry, only cell parameters may give a pseudosymmetry and may mislead the crystal systems. But with the lattice symmetry and cell parameter, we do not have any mislead in defining crystal system. Now, we have in this column a number of independent cell parameters. We will see that this is also a point to be noted, that how we say which one is dependent cell parameter and which one is not dependent cell parameter. You see, in cubic cell, if we define unit cell parameters, we say A is equal to B, B is equal to C, alpha, beta, gamma is equal to 90 degree. What about the number of independent cell parameter here? I showed it, it's only one. Do we get it? Yes, we do get it. You see, A is equal to B, B is equal to C, alpha is equal to beta, beta is equal to gamma is 90 degree. This is a fixed value. But here we get only one value, that is A. If once A is determined, B and C are same. Therefore, we call this cubic cell parameter have only one independent parameter. Similarly, if we go for tetragonal, we see two independent cell parameter. One is A, another is C. If we go for hexagonal, we see there again two independent cell parameter. One is A, another is C. These are dependent cell parameters. This is already fixed. If we go for rhombohedral, you see we get one independent cell parameter, this one, and that is another one is gamma, which is not equal to 90 degree. So this is another independent parameter. So therefore, rhombohedral has two independent cell parameter. Hexagonal has got two independent cell parameter. We come to orthorhombic, we see that there are three independent cell parameter, A, B, and C. Rest are dependent directly. So three independent cell parameter. And then monoclinic, we have these three and one here, four independent cell parameter. And similarly, if we go for triclinic, it has got no dependent cell parameter. It's all are independent. So we have 6 independent cell parameters. You see, if we increase independent cell parameter going down and down and down and down, and here it is 6 independent cell parameter, that it has got least symmetry. And therefore, depending on the cell parameter, the symmetry will be increasing. And here, cubic will have many kinds of symmetry elements. Well, now we go for the next slide. And here, if you know the unit cell parameter correctly, you can immediately find out unit cell volume. And this is a mathematical derivation simple. So here, if we have a cell parameter of cubic, we see that we have cell volume should be A cube. A cube. Similarly, tetragonal cell volume should be A square C, because A and C are the dependent square C. orthorhombic AVC, and so forth. We can calculate all this unit cell volume. Why? One has to remember that in crystallography, length of the unit cell parameter is expressed in Armstrong. To honor Anders Johansson Armstrong, a Swedish renowned physicist, and he is the father of the science of spectroscopy. So to honor him, the unit of unit cell parameter and cell volume are represented as Armstrong. And 1 Armstrong, you know very well, is 10 to the power minus 12 meter. Now, we have been talking already about point group, point symmetry elements, and derived various point group, and also in projection we showed and we took some molecule and show how we can derive the point group, etc. in last lecture, the 4th lecture. But now we have to come to space group. You know, point group and space group are very, very essential to find crystal structure and talk various points of crystal properties, etc. So now we have to go to space group. And when we want to go to space group, we have to also think about space symmetry elements. In point groups, we were talking about point symmetry elements. Now we have to talk space symmetry elements. And there are 2 space symmetry elements. One, we call it screw axis, another we call it glide planes. So how to explain this? This is nothing but that we have a combination of rotation and translation. So if we have twofold rotation and we don't get equivalent position, and we see after a certain rotation in the axis of twofold rotation, we translate, and then we get the equivalent position. That is what is called screw axis. So we have twofold screw axis, threefold screw axis, fourfold screw axis, sixfold screw axis. In a plain, simple, general way, we will say that if we add in point symmetry elements a translation element and we get identical object, those will be the space symmetry elements. So here a twofold rotation and a translation gives us twofold screw axis. Similarly, threefold, fourfold, sixfold. Again, combination of translation and mirror plane gives us glide planes. So glides tend to be axial glide planes, A glide, B glide, C glide, and then we have also diagonal glide planes, that is N glide, and then we have diamond glide planes, that is D glide. Well, this mirror is here, you know, that it's don't have any translational symmetry, but with mirror, if we have translational component, then it becomes glide planes. But double glide planes, we do not consider it very much in the normal crystallographic activities. This is a special, very special, and this is discussed by spatial points in symmetry. Okay, we go to an example. This slide shows an example. I again repeat that if we do not practice it, it becomes a little bit difficult, and we lose our also interest to continue this field. So I request those who are listening it, please go to very different literature, and as soon as you understand it, it becomes very, very interesting for you. to know about crystal structure, crystal lattice, etc. So here I have shown an example of screw axis. This here, you see, a two-fold rotation first, and then I show how a screw axis develop. Now let's say we take a position A, and a two-fold rotation means we rotate it at 180 degree, and then the equivalent position B, we find equivalent position B. You know, then we this is just another point of the unit cell rotating 180 degree, and then we got C. We just compare this with screw axis. Here you see, we start this point, and along this axis we rotate it, and then we don't get this after 180 degree. What we do get, if we translate along this axis of rotation half the way of the unit cell, we get. And that is an example of two-fold screw axis, two-fold screw axis. So here, the same thing we did here, and then we don't get the equivalent position after a rotation along the axis of rotation. After a translation along the axis of rotation, we get simply then we do the same thing. No, not equivalent position. Rotation again half the cell axis, and translation again half the cell axis. We get this. So this is an example of two-fold rotation screw axis, and this is an example of two-fold rotation axis. Just to show you only one example. Now we go for the glide. We said first translation and then reflection. So what happens if it is a mirror plane, and if this is our object, and if we want to have a similar object, we should get this. If we can only execute this mirror plane, we get this object here. Is it not? But in case it is not like this, you see. First we translate, and that position comes here, and then mirror plane, we get the reflection. So this is a translation, and then getting the object again after applying this mirror plane. So this is a glide plane, and we said we could show A glide, B glide, C glide along the axis, cell axis, and then diamond glide, and also N glide, diagonal glide. We get these are the space symmetry elements. What we are talking about. Now we go for space group. How it is that we know very well now, we have 32 point groups. Very well we know that. And also we know we have 14 Bravais lattices. So a Russian, very renowned crystallographer, Fedorov, and a German mathematician, Schoenflies, they derived independently, mathematically, they showed in 1890 and 1891 that there could be only 230 unique space groups for the 7 crystal system. This is a derivation, mathematical derivation for a 3-dimensional object, that how many space groups we could get using these space symmetry elements as well as point groups and Bravais lattice. So what we should remember, those who are determining structure of crystal, 3-dimensional structure determination. Each and every crystal must belong to one of these 230 space groups. Must belong to one of these 230 space groups. Okay, now I showed it how we derive to 230 space group. We have 7 crystal system, add the 7 crystal system to the 14 bar-based lattice or to the 32 point groups, then include this screw axis, that is space symmetry elements, we come out with 230 space group. Now we have to take examples, of at least one example. That let's say a crystal has got point group 2 by n. We immediately conclude this crystal must have monoclinic system, must be monoclinic system. With this point group, the crystal must be monoclinic system. There's no other alternative. But we know also that monoclinic system has got 2 bar-based lattices. One is pre-meeting, another side center lattice. P side center lattice. Using this, if we have point group, this point group, we say you can use point group and bar-based lattice. Then we come to space group. So we have point group here and bar-based lattice here. What would be the possible space group for this particular system? We will have 1, 2, 3, 4, 5, 6 possible space group if we have a point group 2 by n. So we will know why it is P, why it is C in our next slides. But just I showed an example that if a point group is 2 by n, the point group belongs to monoclinic system, and we know monoclinic system has got 2 lattices, only 2 lattices, P and C, nothing else, and therefore with this point group and the lattice type, we can have these 1, 2, 3, 4, 5, 6 point groups for this particular example. We go to next slide. You see, we have to show those space group in stereographic projection. So there we use some symbol of particular symmetry elements, and these symbols are like this. Listen, for point group, triclinic point group, we have a space group 1, that is P1. It has got no symbol. But if we come to a symbol like this, that represents that it is a 2-fold rotation axis. And this is a space with space symmetry element. We have 2-fold screw axis. This is 3-fold rotation, 3-fold screw axis, and so on if we go down this. This is the symbols we will be using in explaining stereographic projection of space group. You might ask that why we need to do this. We'll see that if we want to explain a space group, we need a stereographic projection to explain, and there we find what are the symmetry elements, and as well as equivalent position we have to describe of this particular space group. So therefore, these symbols are very important to note, and we have to remember. We don't think that we need to memorize this. We don't need to memorize it. We will take this in front of us and then explain what is the space group, what are its symmetry elements and equivalent position, where the equivalent position developed. Okay, now we go for the next, go to next slide. It is nothing but a better representation of last slide. You see that when we project in a plane of paper, we can project it parallel to the plane of projection. And the symbol will be like this when it is parallel to the plane of projection. When it is perpendicular to the plane of projection, we symbolize this like this. And here are different symmetry elements, and here symbols, written symbols, and that is the projectional symbols. This projectional symbols. We do need it to explain the space group projection. So you don't need to remember this, just keep this in front of you. Nobody will ask you why you have this in your exam. You can just keep it in front of you and derive your space group, ask space group on this. Okay, here the equivalent position I say. If we have a two-fold rotational axis and it is parallel to A axis, unit cell A axis, then the equivalent position becomes X, Y, Z, and then X, and we call this bar Y, bar Z. In many books, it is written minus X, minus Z, without giving bar, because it may be a bit difficult to type it like bar Y or bar Z. Therefore, many books, you will see that it is minus Y, minus Z. Go for parallel to B, see, just bar X, bar Z, and Y, equivalent position. X, Y, Z, equivalent position will be this one. Okay, and parallel to say, see, it is like this. And if we take up screw axis, and if it is two-fold screw axis parallel to A, the equivalent position will write it like this. And B, equivalent position write it like this. See, this is all this. So I need not to explain every point here. I simply show you that these thing we need when we have to explain a particular space in stereographic projection and in a plane of in a paper, two-dimensional plane. Okay, so we go to the next one. Now we are talking about space group. We discussed the space symmetry element, space groups, etc. But a crystallographer must understand the stereographic projection of space group. I will take the stereographic projection of 2 or 3 space groups to show you and some rules in the next lecture. Thank you for your attention for the 5th lecture of chemical crystallography in solid state chemistry. Thank you very much.